So Scala 3 is on the way. It's currently called Dotty, but at some point it will become Scala 3. And in theory, it'll be out this year, but we'll see. It's bringing a lot of exciting features, but some that have really caught my eye are around type class, generic derivation, and meta programming using macros. So I'd like to give you a little tour of how that's going to look. And along the way, we're going to see a few other Dotty features as well, and some new syntax as well. So first, we're going to just quickly recap how type class derivation looks currently in Scala 2. Then to get a bit of context, we'll compare with some other languages. We'll see how things look in Haskell and in Rust. Then I'll explain what Scala 3 offers in terms of type class derivation. Then we're going to jump into some live coding. I'm going to implement generic derivation of show, which is probably the world's simplest type class. It takes a thing of a given type and prints it as a string. I wanted to show you Functor as well, but I don't have time for that, unfortunately. But there is code available in the repo for this talk, so I'll give you the link later and you can browse at your leisure. And finally, I'm going to show an example of where generic type class derivation interacts quite nicely with the new metaprogramming framework using macros in Scala 3. So how things look currently in Scala 2. Say you are a library author and you want to offer some type classes in your library, and you want users to be able to automatically derive instances for their data types. You can provide generic derivation in a few different ways. Probably the best option these days is to use Magnolia. Originally, Shapeless was the library of choice for this, but these days Magnolia has probably a nicer API and it's optimized for very fast compile times. Shapeless still has a lot of extra cool stuff that it does, but in terms of type class derivation, Magnolia is probably the way to go. And there's also the option to not use either of those and roll the macros yourself from scratch. And I've done that and I wouldn't really recommend it, except in very extreme cases. In terms of how users actually enable this generic derivation, how they opt into it, there's a few different patterns that have evolved. The first is to define your generic derivation methods in the type class's companion object. And that means that the user doesn't need to opt into it, it's just enabled automatically. But on the other hand, it means it's very difficult to opt out of it as well. If they are worried about generic derivation slowing down their compiles, or there's a few other reasons they might not want to use it, it's quite difficult to turn it off. So an alternative is to do what libraries like Circe do. Circe requires the user to opt in using an import. So they can import generic.auto._, and that means turn on auto derivation completely. Wherever you can, use it. Or if they want a bit more granular control, they can import semi-auto, and then they can specify exactly which instances they want to be auto-derived. Haskell has been doing generic derivation type classes for years now. It's a very mature feature. It has a keyword called deriving, which you can add onto your data types. We saw some examples in Pavel's talk earlier. And that, if you use this deriving keyword, then the compiler can automatically derive a few stock type classes, things like show and equals and a few others. On top of that, there's a whole zoo of different language extensions that you can enable, which let you derive different type classes like functor and traversal and generic and so on. There's also a recently added extension called deriving via, which is extremely powerful. And I will show you a few examples now. So here we have a few examples in Haskell. We've got a data type here called user. This is a sum type. It's got two different cases. It might be a logged in user with an ID and a name, or it might be an anonymous user with no fields. And you can see we're deriving show and equals here. So these are available out of the box. You don't need any language extensions. Then we have a higher kinded data type. So this foo data type has a type parameter A, and we've got a foo which has an A field and a string field. So A might be int or string or whatever. And because it's got this type parameter, that means that we can derive functor, so we can map over this type. And in order to do that, I've added the derived functor language extension at the top of the file. So an example of using that, we've got a foo here with 42. So the A type is integer here, 42 and hello. And then because we have an instance of functor available, we can use this map operator here to map over that foo using a function that adds 1 to it. So we end up with a foo of 43 and hello. Finally, an example of deriving via. We have a new type here, which is a zero cost wrapper around another type. So we've got an integer, but we want to wrap that into a domain specific type that we call price. And because semigroup is already available for summing integers, like this, sum int, we can reuse that using deriving via. We don't need to bother writing our own semigroup. We can just say, make a semigroup instance that's the same as this one. So that's quite useful. And you can do much more fancy things using deriving via. This is a very simple example. There's a few examples down at the bottom. I won't bother running them. You'll just have to trust me. And the code is all available on GitHub if you want to play with it later. Onto Rust. Rust is obviously a later language than Haskell, and is clearly being inspired by Haskell. It's the same kind of idea, but the technical approach is a bit different, and obviously the syntax is very different. So instead of a deriving keyword, you add this, this hash thing onto your data types. This is called an attribute in Rust. I guess this would be an annotation in Java or Scala. And you use this derive word and you say which traits you want to derive. So just like Haskell, the compiler can automatically derive things like equals and debug, which is similar to show. It's got a few stock traits that it can auto derive. But if you want to derive other traits, say traits that you've defined in your library, and you want to provide auto derivation for those, you can provide macros to do that. So we can have a quick look at that. So I've got a struct here, person. This would be a bit like a case class in Scala. It's got a name field and a height. And you can see it's got this derive annotation on here. So out of the box, we're deriving debug, partial equals and equals. And then this one, implement height. This is not the name of a trait. This is the name of a macro that we've provided, which will do more derivation. So if I show you the macro, so over on the left here, we've got the actual macro implementation. So we've got a function called derive height. You can call it whatever you like, as long as it's annotated with this special attribute called proc macro derive. And here is where you decide the name that you want to register it with. So this name here matches the name over on the right-hand side. The input to the macro is this thing called a token stream, which is as bad as it sounds. It's just a raw stream of lexical tokens representing the struct person that's been annotated. Luckily, somebody out there in the Rust community has already done the hard work, and they've provided this library called syn, which can parse that stream of tokens into an AST. But So you have access to the syntax tree, but you don't have any access to types. So in that sense, macros in Rust are a bit more primitive than those in Scala. The output, the return type of this macro is another token stream. So the way this works is we parse the input into an AST, we extract the name of the struct from there, and then we just construct our result as a string. So just a string containing some Rust code. And we construct an implementation of the height trait for whatever the name of the struct was, person in this case. And here we have the actual implementation of the method that we need to implement. So that's how it works in Rust. So in Scala 3, what new features do we have? First, we have a keyword called derives, which is remarkably similar to what we just saw in Haskell and in Rust. You can annotate your data types with this new derives clause and say, I want the following type class instances to be derived for me. And the other feature that we're going to make use of in a second is this thing called mirror. As the name suggests, this is all about reflection, but this is compile time reflection, not runtime. The idea of mirror is that it gives you just about enough information about a given type in order to write your write your type class instance and no more. So if you're lucky, I guess for 99% of type classes, you'll be able to get by with just mirror, and you won't need to reach for the awesome and terrifying power of macros. So let's have a look at how this derives keyword works and how we can use a mirror. We're going to try some live coding. Before we start, I'll just give a warning or just quickly say, I am going to move quite quickly, and there's a lot of new concepts and also a lot of new syntax. So if you haven't seen any Dotty code or Scala 3 code yet, you might be quite overwhelmed, but don't worry if you don't understand every last detail, just try to get a taste of what this is going to look like in Scala 3. Also, I think there's a break just after my talk, so you just need to watch me flail around in Vim for about half an hour, and then you can go and have a lie down. Let's just close that, get rid of these. Okay, so let's make a show type class. How do we make a type class in Scala 3? Pretty similar to Scala 2. Sorry about the sirens. It's going to be a a trait with a type parameter. I'll call it A. And if this was Scala 2, I would write this as a method show, which takes a value of type A and returns a string. That's perfectly reasonable. So in order to use this, say we had a case class person with a name. I would summon an instance of the type class. I would call show on it and pass in a value of type person. And that works fine, but it's kind of the wrong way around in a lot of cases. What you want to do is you have a person and you want to call .show on it rather than getting the type class first and then passing a thing to it. You want to do it this way around. It's more kind of object-oriented style, I guess. And this is possible to do in Scala. You can use implicit classes to add these extension, they are often called syntax, onto other types. Cats does this, but it's kind of boring to write, and it's quite a lot of boilerplate for the library maintainer. So luckily in Dotty, this is much easier. Extension methods are now a first-class feature of Dotty. So we can write this as an extension method instead, like this. The syntax looks kind of weird at first, but you get used to it. So this says for any type A, which has a show instance, we can add this show method to it as an extension. So now we have a show type class. Let's go and have a look at our data types. Over here, I've got a pet on the top left. I've got a person on the bottom left and an employee on the right. So for case classes, you can add this new derives keyword. It goes after the arguments. We're going to derive show. Do the same one down here. And then enums. So this is a new feature of Scala 3. In Scala 2, if we wanted a sum type like this or an enumeration like this, we'd write it as a sealed trait with a case class and a case object for the different cases. But here we can write it as an enum, so it's much more concise. It's pretty much the same idea, it's just much more friendly syntax. In the case of an enum, we put the derives up here. So this is an enum with two different cases. One has some arguments and one doesn't. It's worth noting it's actually a recursive data type as well. So an employee can contain another employee as a field. And this pet over here, this is like a nested ADT. So it's a case class that contains a field which is also a case class. So we've covered most of the different patterns that you might encounter with ADTs in Scala. So let's try compiling this, see what happens. Oh, yeah, I did add show to all of them. Okay. So it's complaining about the derives show keyword. It says value derived with a D at the end is not a member of nonsensical no type. What this actually means is value derived is not a member of show. So it's looking for some method called derived with a D. Why would it be doing that? And the answer is this derives thing, this new derives clause, this is just syntactic sugar. What the compiler is doing is creating a companion object for our data type, if there isn't one already, and it's adding a given. Given, this is a new thing in Scala 3. You can think of it as an implicit val in Scala 2. So it's creating an implicit val in the companion object. So it's saying, here's an instance of show for the pet type, and the implementation, the way it calculates this instance is it calls show.derived with type pet. So the compiler just assumes that the show, the type class, will have a companion object, and in that companion object there will be a method called derived with one type parameter which does the right thing. It returns an instance of show for pet. So it's our job as library authors to go and write this derived method. Let me just delete this because the compiler is going to write it for us. And we'll go back to our show. We need a companion object. And let's try just writing this derived method and see how it goes. So it needs to take a type parameter, and it needs to return a show of A. So return a new show. And it needs to implement this show method. And for now, let's just put a placeholder and see what happens when we compile. Okay, compile works. And if we run, oh, actually. I'm going to update my main method. I'm going to create a person and a pet and an employee. I'm going to make a little helper method called showMe. So this says for any type A, which has an instance of show, give me an A and I'll return you a string. And it's calling the show extension method on the value A. So if we print out our 3 shows and we run this, we get to do 3 times, which is what we expect. So you can see that it's calling our derived method as we hoped it would. Okay, so how can we go from a derived method that just says to do to an actually useful derived method that will print out a nice pretty printed version of whatever A you give it? Because I have time constraints, it's now going to be less live coding and more live uncommenting. So I'm going to go down here. We already have a trait show. Let's uncomment the object and some imports. Okay, so here is what our derived method is going to look like. Suddenly it's inline. We'll come back to that and what it means later, but we have a def derived type parameter A, and it's using a mirror of type A. Using, in Scala 2, this would be implicit. So it's summoning an implicit instance of this mirror of type A. And it's returning a new show. So what is it doing? It is doing an inline match. Ignore the inline again, doesn't really matter, but it's doing a pattern match on the mirror and looking at whether it's a product mirror or a sum mirror. So what's that all about? Let's go back to our data types. Here we have the case class pet on the left-hand side. This is a product type. Its case classes are made up of a number of fields, so it's known as a product. It's a category theory word, but this is a product. And then enums over on the right-hand side, where you have a choice between a number of different cases, like it's either a grunt or a CEO, that is known as a sum type or sometimes a co-product. So enums are sum types, case classes are product types. And when you have an ADT, an algebraic data type, everything is one of those two. It's either a sum or a product. So when we're given a mirror, we know that the thing is either going to be a product type, like a case class, or it's going to be a sum type, like an employee. So we pattern match on the mirror and treat each of those two cases. So let's start with product. So we're going to make this method show product, which takes the product mirror and it takes the value A that we're actually trying to pretty print. So we have this def show product A, takes the product mirror, takes an A, returns a string. And what do we want to actually return here? So let's say we had a case class. We'll go with a pet. No, actually we'll use a person. So let's make a person with name Chris and height 180 centimeters. What would we want to do if we did Chris.show? We'd probably want the class name. So we'd want person. And then we'd want to print out each of the fields. Might be nice to have the field names rather than just the values. So we'd have name equals Chris and equals 180. Comma separated list of fields. That's what we're aiming for our show implementation. And here we just have an int and a string, so we could probably just two-string them. It would probably work out okay, but let's say we had pet, which has a person as its third field. So we'd probably, in cases like that where we have nested case classes or more interesting types, we'd want to use show instances for those nested, those field types. So we'll want to be able to summon show instances for the types of each of the fields. So we need the name of the product, or the class name here, and we'll need for each field the name of the field, the show instance for that field's type, and the actual value, Chris. Let's have a look at how we can use a mirror to get each of those things. So first, the name of the class or the product. We're going to use this thing that we can get from the mirror called mirrored label. So this is the name of the thing. This is person in this case. But the interesting thing about this is that it's not a string, it's a type. So where you might think it would be something like person, it's not. It's actually the singleton type of that string. So it'd be something like this. I'm not sure exactly how you write it, but this is the idea. It's a type, it's not a value. So in order to get the actual value that has that type, you can use this magical method called const value. You give it the type, m.mirrored label, and this will give you back the actual string. So it'll give you person as a string. And in order to use this magical thing, this const value, which only works at compile time, you need to mark your method as inline, because it's actually going to run that compile time, if you see what I mean. And because show product is an inline method, that means this match needs to become inline, which means that this derived method needs to become inline. So if you're using Scala 3, you often find that the word inline kind of spreads all over the place. You'll see it everywhere. Right, so we have the name, and then for each field, let's get the field names. Again, we're going to use the mirror. We're going to use this member of the mirror called mirrored LM labels. Again, this is a type, not a value, so we need to extract the value out of it somehow. And the type of this is actually a tuple. So it's kind of like a tuple of singleton string types. So it'd be like name.type and height.type. We're going to implement a little helper method called lm labels to get that information out of the type and turn it into a value. So that is up here. Inline def lm labels, it takes a type t, which is a tuple type, and returns a list of strings. And we are going to use another magical method called erased value. So we give it the type t, then we call erased value and we match on it. And this allows us to actually match on the type t. So we need to handle two different cases. Unit means an empty tuple. So we've got to the end of the tuple, so we just return an empty list. And then the more interesting case is this one here, where we deconstruct the tuple into a head and a tail using this new syntax, this operator here. So we've got the first element of the tuple, which is this type t, and then we've got the remainder, which is this tuple type ts. Here we use const value again, give it the head type t. So that gives us the value which has that type, the one and only value with that type. So in the first field, it would be name and as a string, and then the second, it would be height as a string. We have to cast it here, but this is a safe cast. The compiler doesn't know that this is a string, but we do. So this is fine. It's unpleasant, but it's safe. So we've extracted the first string from the tuple, and we recurse on the remainder. This ts is the remainder of the tuple, the tail. So we call ourselves recursively with the remainder until we get to the nibble case. So at the end of all that, we end up with a nice list, which is going to be a list containing these two strings, name and height. Next, let's see how we can get the show instances for each of these types. So the two fields that we have are a string and an int. So we'll need to look up or summon show instances for int and string. We're going to make another helper to do that, which I've called summon all, and it's very similar to the LM labels. It's the same idea. We match on the type T, and we iterate through it recursively. But in this time around, when we have a type T, we use a function called summon inline, and we use that to look up a show instance of type T. So this would be show of int or show of string. And then we add that as a head of the list, and we recurse through the rest of the tuple. So the result of all of this, we'll have another list, but it'll contain a show of string and a show of int. And finally, for each field, we need to get the actual value of it so that we can print it out. We have the value A, the actual person that we're trying to print out. And because we have a product mirror, we know that A must be a subtype of product. So we can safely cast it here. We can say A is a product, and that means that we have access to this thing called product iterator, which just gives you the different values of the fields in the product. These will all have different types like string and int and so on, so you end up with a list of any here. So this will be a list containing the actual field values like Chris and 180. So we've done all the hard work, now we just zip those things together and produce some strings. So for each field, we make this string that has the name of the field, equal sign, and then we use the show instance to call the show method and pass in the value of the field. And finally, we construct everything into one big string. Okay, I hope you're still following me. There was a lot going on there, but we've now successfully done the product case, and we can move on to the sum case. So just as a reminder, a sum is something like an enum or a sealed trait hierarchy where you have a choice between different cases. So we're going to have this show sum method. Here we're using a sum mirror, and we have the value A that we're trying to print out. And because we have a sum mirror here, we have access to this method called Ordinal, which tells us which case, the number of the case that we are dealing with. So you pass in the actual value A, and it will tell you which case of the sum type this is. So sum types have their cases numbered. Let me just close these ones because it's falling off the side of the screen. So this enum has these two cases, and they will be numbered starting at 0. So this is the 0th case, and this is the 1th case, the first case. So this thing, you give it the value, and it's going to tell you this is either a 0 or a 1. So the way this show sum works is it's going to iterate through the tuple of different types that, that the element might be. So it's either a grunt type or a CEO type. We iterate through that tuple, which is this mirrored element types here, until we get to the correct index, either 0 or 1. When we do that, we can use the show product, which we've already written, to actually produce a string. So let's go through this. Here we have n, which is the index that we're currently looking at in the tuples. That starts at 0. Ord is the index, the ordinal that we're trying to get to. and A is the value that we want to print out. So the same story as usual, we match on the type T, we deconstruct the tuple into the head and the tail, and then if we are at the right place in the tuple, so if n equals ord, then we summon a mirror for type T. So the way ADTs work is that if you are looking at the different cases of a sum type, you know that each case will be a product. You can't have a sum made up of sums. It doesn't make sense, or in Scala at least. So you know that it's going to be a product, which means that you'll be able to summon a product mirror for that type T. So we summon that, and then we use it, we pass it into show products method that we wrote just now. So that's the method up here. So we delegate the printing to this show product, which we've already written. So that's what we do when we've got to the right point of the right index in the tuple. Otherwise, we haven't got there yet. So in the else case, we just recurse. We increment n, and we recurse over the remainder of the tuple, this TS type here. So we've done sum and we've done product. So if I save this and we run again, let's see what happens. Actually, we'll try and compile first. Okay, so it failed because it can't find the show instance of string. So it's trying, clearly it's trying to find the show instance for the first field of one of the case classes, which is the name field. So it's looking for show of string, can't find it because we haven't defined it. So let's just quickly define some type class instances for int and string. If it's an int, we just call toString on it. If it's a string, then we wrap it in double quotes. So now it should compile. And if we run, it prints out what we hope it would. So for a person, it prints out the name field and the height field, comma separated. For a pet, we've got the name, the species, and then the owner field, which is of type person. You can see that it's using the show instance for person, which is what we wanted it to do. And for the employee, we can see that it's a grunt whose boss is a grunt, whose boss is the CEO. So it's working fine with recursive data types as well. How am I doing for time? Not great. Okay. Right. So that was how to do type class derivation using mirrors. It was a reasonably simple example as far as type classes go. As I said, there is a more complex example for Functor, which is available on GitHub, and I'll share the code later. Now, I'd like to look at a use case where mirror is not sufficient for our needs. So we need to use macros instead. So we can have a quick look at the new meta programming framework in Scala 3, see what macros look like. Before we dive into the code, I need to quickly explain what the use case is all about and give you a bit of context. So in my day job at 47 Degrees, I work on something called Mu, which is a framework for building microservices. The idea is that it makes it very easy to spin up a new service. We take care of lots of boilerplate for you. One of the features that we offer is automatic generation of gRPC clients and servers. And the way that we do that currently is using a macro annotation. And macro annotations are going away in Scala 3, so we needed to come up with a replacement for this mechanism that we have at the moment. The way it works at the moment in Scala 2, ideally you start with a definition not in Scala. This is in protobuf, so it's a nice language agnostic file format that you can easily share with other teams in your organization who might not be using Scala. Here's a very simple example. We've got a gRPC service called greeter, which has one RPC endpoint called say hello. It takes in a hello request and returns a hello response. If you've got this file, you need to write a corresponding service definition in Scala. You can write it by hand if you want to, but we recommend that you use our SBT plugin to generate this code. And the Scala definition looks like this. So the request and response become just normal case classes. And then the service becomes a trait with a say hello method. And it's annotated with this service annotation. And currently this is a macro annotation. So when that macro annotation gets expanded at compile time, it generates a companion object for your service. And in there, it adds a bunch of auto-generated factory methods for use on both the server side and the client side. So on the server side, there's a method a bit like this. So given an implementation of the greeter service, so it's your job as the library user to actually write an implementation of the greeter trait that contains your business logic. Assuming you've done that, you can pass it to this function, which will convert it into a gRPC, this thing called a server service definition. And once you've got one of those, it's very easy to expose that as a gRPC server. Then on the client side, given a host and a port that you want to connect to, we can generate an instance of the greeter trait, which will actually make the remote call to the server and send a request and deal with the response. The macro annotation is doing quite a lot of stuff behind the scenes, but in general, what it's doing is it's iterating through each of the methods in your trait and mapping each one to an RPC endpoint. And it's also taking care of protobuf serialization of your requests and responses. So in Scala 3, the plan that I came up with, it's still kind of proof of concept at this stage, is to move the factory methods out of the auto-generated companion object and put them in type classes, and then derive instances of those type classes using macros. And the reason that we need to use macros and we can't use a mirror is that we need to iterate through the methods in the trait, and mirrors don't give you access to that. So here's an example of what the type class might look like for server-side factory methods. I called it gRPC server-side, and it adds this extension method to your service. So you've got an implementation of your service trait. You will get this extension method added to it, which will turn your service trait into a gRPC service definition. And similarly, on the client side, you can call this client method, give it the host and the port, and it will give you back an instance of the service trait. So the first step of the process looks very similar to how it does now, except that the Scala code now has the derives clause, and it's deriving the server-side and client-side type classes. Then as a user of the library, what you need to do is first implement the greeter trait, implement your service. This is where all your business logic goes. Once you've done that, you can call this extension method that we've added onto it, and that gives you a gRPC service definition, which you can then expose as a server. And on the client side, if you want to connect to that server, you can use the gRPC client-side type class and call .client on it and say where you want to connect to. And that will give you an instance of greeter. That's the plan. And I can show you a quick walkthrough of the code. I'm not going to go into this in too much detail because time and there's just a lot of complexity here. There's too much to explain. It deserves its own talk, I think. But you can see how we have the trait here, the companion object for the trait, and then we have our derived method. And you can see it's got this weird splicey syntax here, which means that it's calling a method. It's calling a macro. So it is calling a macro, which is called gen. And that gen is defined down here. So gen implicitly takes a quote context, which is similar to black box context or white box context. If you've ever written macros in Scala 2, it should be quite familiar. And it's immediately importing quote context.tasty._, which means that it's using a new feature of Scala 3 called tasty reflection. And that means that it will be able to introspect this type S that we're given, which is the type of the service. And it'll be able to look up things like the class symbol for that type. And from there, it can get a list of the methods that in that class and iterate through them, which is exactly what we need to do. So this is the meat of the macro. It's grabbing the class symbol out of the tasty tree. It's doing a bit of validation to check that this is a reasonable class that we should actually run the macro on. Has it got the right annotation and so on? And then it is looking up the methods in that class. So it's got a list of methods. It iterates through those. And for each one, it is creating a gRPC method definition, which will actually call your code in order to handle a request. So when a request comes in, it'll pass it to your method implementation. You'll return a result, and then that will get sent back to the client as a response. So that's this part. And then it is implicitly summoning protobuf serializers for the request and the response as well. So we end up with a list of these method descriptors or method definitions. And then down at the bottom, this is the actual result of the macro. You can see there's this quote and then curly brackets here. So we're returning a so-called quoted expression. And inside this quote, we are constructing a new instance of the trait, of the type class, sorry. And given an instance of your service, your greeter, it's building up the service definition and adding all of the method definitions into it. So there's a bit of gRPC jargon, which may not have made much sense there, but I can just very quickly give a demo to prove that this works. That started at a port on server on port 8080. I've got a gRPC client here. So if I send a hello request with the name Chris, my server will respond, hi Chris. So we covered an awful lot of ground there. Just to summarize quickly, we saw how the derived clause can be added to your data types, and that ends up calling a derived method in the companion object to the type class. We saw extension methods, a new feature of Scala 3, how they're quite handy sometimes. We saw how implicit has been replaced by these keywords using and given. We saw inline all over the place, which I didn't really explain very well, but at least you got to see the keyword exists. We saw an example of deriving the show type class using a mirror, and an example of deriving a more complex type class using a macro. The slides are online, the code is online. I may well have gone over time, so sorry about that, but thank you for listening.